Okay, Assalamualaikum warahmatullahi taala wabarakatuh, and a very good day to all. Alright, today we will proceed the last the last topic in week 9, which is right. So this is your CI. Okay, so this is your CI, and we have covered the Ampere's circuital law. Okay, we have covered the Ampere's circuital law, and also we have discussed some of the example, right? And today we will proceed by introduction to the curl concept, Stokes theorem, and magnetic flux density. Okay, so so right, so you may download this lecture note in your e-learning. All right, okay, so please refer to this to your lecture note in e-learning. All right, so first of all, okay, in this lecture, okay, I will explain more about the applications of curl and Stokes theorem. Okay, curl and Stokes theorem. Okay, the introduction for curl and Stokes theorem is explained quite detailed in the Sadiko book. If you have the Sadiko book, okay, or if you have any other reference book, okay, usually they're gonna have the first or basic explanation about the Stokes theorem. Okay, so based on Sadiko books, okay, you can refer to the page of 85. Yeah, it's explained detail in these pages. Yeah, and for today we will in this video I just explain about the application of curl and Stokes theorem in magnetic field. Right, so let's imagine that we have a line. Okay, let's imagine that we have a line here. Okay, where this line here carries a magnetic field intensity H. Okay, and let's say that we want to analyze the behavior of the field, okay, behavior of this field regards to the curl model. For example, at this specific point, we want to analyze the behavior of the field, okay, regards to the curl model, all right? So we want to analyze H based on, since that the topic now is we are discussing about curl, so based on curl model. Okay, so how we want to represent it? Okay, so it can be represented by this symbol, which is this is the the del notation. Okay, so this is the del notation cross with the H, which is the magnetic field intensity. Okay, so how to pronounce this expression or this formula? We will say that this is curl of H. Okay, curl of H. Okay, and this notator is a del notation. Yeah, but when it's combined, when it is crossed with H, we called this expression, okay, as a curl of H. Right. So of course, with our experience from a previous chapter we have learned, okay, so this del notation or this curl of H, we have to what if you want to use it, you have to suit this expression depending on what kind of orthogonal coordinate system, right? Either it is Cartesian or cylindrical or spherical. So you can see now that from what we have learned before, it is always connected to each other. Okay, so if you have the Sadiko book, the Cartesian is expressed in equation in page 85 as equation 3.44, cylindrical equation 3.45, and spherical equation 3.46. However, if you don't have the Sadiko book, not to worry, I have put this is the equations here. Okay, so this is referring to the Cartesian, this is referring to the cylindrical, and this is referring to the spherical. Okay, and you can found you found that this is represented as A. So now, since that we are dealing with the curl of H, what you have to do is you have to replace this A, okay, vector of A here, with vector of H. Okay, you have to you have to suits, yeah, this equation, okay, this general representation with the one with curl of H representation. Okay, so here will be HZ, HY, HX, HZ, HY, HX. Okay, so this is a general representation curl of A. So if you want to calculate curl of H, you just have to make it change the A with H. Alright, so I hope this is very clear. So now, since that I said that we want to discuss more about the application, let's look at the application. Okay, so these are the previous application that we have. This is the previous example that we have discussed before, if you still remember. Okay, so assume that this is we have a cylindrical with the length of the cylindrical is infinity. Okay, we have, that's why there is a noted line here, and the radius of the cylindrical is A, and it has a total current where it is I. Okay, the value of the total current. So from previous example, we know that, okay, where Hi in H1 in region number 1 is where R is lesser than A is equals to IR over 2 pi A squared at phi direction, and in region number 2 where R is larger than A, which is the radius from the cylindrical, okay, is equals to I over 2 pi R, and also at the phi direction. And if you still remember, I have drawn the graph which is based on H and R, right? If you still remember. Okay, now with the same question, we want to determine curl of H in both regions. So instead of using this type of calculation, I want to use the curl. I want to find the curl of H in both regions. Okay, from this answer, I want to proceed my calculation to define or to determine the curl of H for both regions. Okay, however, from the previous answer, which is at region 1 and at region 2, what we can say that since that the value of the magnetic field intensity only involve at phi direction, so we can say that H at z direction equals to H at r direction, which is equals to 0, right? And this phi direction, we can say that since that it is on a phi direction, we can say that this is also, okay, IR over 2 pi A squared at region number 1 is also equals to H phi. Okay, H phi at region number 1 is equals to IR over 2 pi A squared. And H phi at region number 2 is equals to, this is H phi at region number 2, this is at region number 1, this is at region number 2, is equals to I over 2 pi R. And H at z direction and H at r direction is equal and equals to 0. Okay, and now we want to determine curl of H for both regions. So let's try to solve it. Okay, so I would like here solution. Okay, so solution. So since that this is our the shape of our problem now is a cylindrical shape, so of course we will refer to the curl equation, this equation, right? Curl with cylindrical representation, right? So curl of H, curl of H, okay, is equals to del notation cross with H, H vector, or we can say that this is the curl of H. Okay, same as equation 3.45 if you have the Sadiko book. Okay, and if you don't have, equal to, you can refer to the handout in previous page. Yeah, if you don't have the book, so it's equals to 1 over r dHz over d phi minus dH phi over dz at r direction plus dHr over dz minus dHz over dr at phi direction plus dr h phi over dr my dhr over d phi at z direction. Okay, this is the the curl of H for cylindrical shape. Yeah. So now let's, since that we know that for Hz and Hr is equals to 0, so therefore for this differential, it will becomes 0. Okay, and this H phi, okay, for region 1, okay, for region, now let's solve for region 1 first. Yeah, this H phi for region 1 will be I r over 2 pi a, and dhr, so since that this is equals to 0, so all of this will be 0, and dhz also will is equals to 0, so this is also equals to 0, and this h phi will, since that we are dealing with region 1, yeah, I put here region 1, yeah, solution for region 1, so that we will not confuse. So this, the value of here is also IR over 2 pi a squared, and this HR is equals to 0. Okay, now you can say that our calculation will involve only this part, this one cancel, and also this part, right? So now let's rewrite the equation. Okay, for region 1, okay, curl of H y is equals to, okay, so r directions, it will be, since that this is equals to 0 and this is over dz and there is no z here, so although this is have some value of however it's over dz, and therefore this is also equals to 0, right? So 0 at r direction plus 0 at p direction plus, okay, so now this is r and over dr, so there are going to be some value here, so it will be 1 over r d over dr ir over 2 pi a squared, and this is equals to 0. Straight away it's going to be out at z direction. Okay, so if we solve this mathematics, we will get that it will be 1 over r, okay, 2 ir, okay, because this is ir, okay, the differential of ir, okay, ir, so it will becomes ir, what ir, yeah, the differential of 1 over r, it will become, so we will bring 2 in front here, 2ir, okay, 2ir, yes, 2ir over 2 pi a squared, right? 2 pi a squared at z direction, and this this I will remain, yeah, I will remain, r and this r will cancel each other, this 2 and this 2 will cancel each other, so it will leave behind only I over pi a squared at z direction. Okay, I over pi a squared at z direction, and this answer, okay, related to this answer, let's say that for this part of cylindrical, we want to determine the j, yeah, the j. So what are the formula? What is the formula? The formula is to, if you want to determine j, yeah, total current, this is the formula, right? The total current over total area, okay, and what are the direction of j? So now if you see in this diagram, the total current is, the direction is z direction, so it's going to be on the z direction, okay, because in this diagram the current direction, the total current direction is same as z direction, so it will be on z direction. If you are referring to other questions, you have to look where are the total current directions, yeah. So these are the formula, total current over total area at z direction. So in these questions, the total current is I, right? And the total area is what? Pi a squared, right? Pi a squared at what direction? At z direction. So you can see here, if you want to determine j at this part, at j at region number 1, j at region number 1, okay, based on this formula, we can compare, the answer is I over pi a squared at z direction, and we can compare, the answer is actually same for curl of h for region 1, which is, the answer is I over pi a squared at z direction. So we can say that this answer is actually equals to J, okay, which is the volume current density. Okay, J is what? J is a volume current density. Okay, volume current density, or source of the field, which is source of the field. Yeah, source of the field. Okay, so we can see at region number 1 that the final answer of curl of H is same with the volume current density or source of the field. All right. So now let's do for region number 2. How about for region number 2? Use a different color here. So for region number 2, okay, so the curl of H is equals to, okay, of course this is going to be same, 0 0. The only difference is the value of H phi inside here. All right, so it will be I over R d over dr. So what other value is I over 2 pi R, right? And at the Z direction here. Okay, at Z direction here. So, okay, so the differential of R here, it will be R1 over R, so it will be no R, right? So there will be no R here, the differential of R. So it will be, it will be I. Yeah. Oh, there is R here, right? There is R here. Sorry. So for this also, this should be R squared here, right? I'm so sorry for here. There's a because this R is times with this R, so therefore there will be R squared here. So R squared. So when you different, you will bring 2 in front here, IR. Okay, I'm so sorry here. Okay, this is supposed to be IR squared. Okay, so when you different this value, it will be 2IR. Okay, 2IR here. Yeah. So here, since that there is R here, so it will be IR, and this R and the down part of this R, it can be cancelled to each other, and therefore there will be no R left behind here. So the differential later on will equals to 0. Okay, and will equals to 0, and therefore if we want to compare the J at region number 2, J at region number 2 here, so this is J at region number 1, J at region number 2. Since that there is no current here, so J at region number 2 also equals to 0. And you can say that this is also equals to J at region number 2. This is J at region number 1. So you can see that the curl, well, what we can say now, we can say that the curl of H is always equal to the volume current density, which is J. Alright, and we can rewrite that curl of H is equals to J. Okay, and finally we can write curl of H is equals to J, and this will give us this, yeah, will give us Maxwell equation. This is the Maxwell equation number 3. Okay, we have discussed Maxwell equation number 1. We have also discussed Maxwell equation number 2, and this is now I introduce to you Maxwell equation number 3, where curl of H is always equals to source of the field, which is the volume current density. Okay, where source of the field for magnetostatic field is the total is the volume current density. Okay, so this Maxwell equation number 3, we can compare with Maxwell equation number 1, if you still remember Maxwell equation number 1, where del notation dot product with the magnetic electric density is always equals to rho v. And what is our rho v? Rho v is also the source, right? Source of electrostatic field. Okay, so we can say that, and this is also J is also the source of magnetostatic field. So we can say that Maxwell equation number 3 and Maxwell equation number 1 gives us that the product of from the product, yeah, is the end product, the final product is always equals to the source. Okay, whereas for Maxwell equation number 1, this is Maxwell equation number 1, it gives us the source of electrostatic field, and Maxwell equation number 3, it gives to us source of the magnetostatic field. Okay, so this is what of the the curl the curl of H. All right. Okay, now let's discuss about the Stokes theorem, and before that, I would like to wait, yeah, I will like to include some. Okay, so this is gonna be our Stokes theorem. Okay, now we want to entering the Stokes theorem. Stokes theorem. Okay, so what is the Stokes theorem? Okay, Stokes theorem. Okay, the definition of Stokes theorem is to convert, yeah, to convert one format to another format. Okay, for example, you have a line the line current, so we want to convert that particular line current to surface current, so we can apply or we can use this Stokes theorem. Okay, so for example here, okay, from Ampere's circuitry law, from ACL that we have discussed earlier, we know that H, okay, close loop, okay, H, which is the magnetic field intensity, dot with dl, which is the displacement, is always equal to I and close, and this is applicable for line field, right? And this is also equals to integration of volume current dot with the area, okay, dot product with area. And we have discussed before from the previous slide, J is also can be represented as del cross with H, or we can say curl of H, which is equals to J, okay, which is equals to J. And this is for line current, right? This is for line, and this is for surface because it is involved with S, right? Involved with surface. So this is its surface. So this is line. So this is two. We are converting. Okay, we are actually converting from the line field to the surface field, and from here we can rewrite our equation, which is this. I'm right S here is which is referring to the surface, and L here which is referring to the L, which is equals to del cross H dot ds now. Okay, dot ds now. So now we can say that we are able to convert line integration to surface integration. Okay, and this can be done using the Stokes theorems. Okay, and how about from surface to volume? Okay, of course we can also done that based on the divergence theorem. We can convert from surface, okay, d dot ds equals to v, where where del dot d over dv. And this is sorry, delete this one, okay, and this is based from the what electrostatic field, right? So based on the electrostatic field, we can convert surface to volume, and based from magnetostatic field, using the Stokes theorem, we can convert from line to surface. Okay. Okay, now, so this is basically about Stokes theorem. Okay, so you can where it shows that from the line from the line integration, you can change into surface integration. But what are the information you needed is you have to have the information of H, and you have to know the ds surface, yeah. And for the line integration, you have to know the H and also the displacement area, yeah. Okay, now let's compare the magnetic field density and the electric field density. Okay, so magnetic field density is represented to B, and electric field density is represented to D, right? This is what we have learned before. Okay, so now since that we said that magnetic field is same, yeah, as electric field, but only the symbol is different, only the terms might be quite different. For example, in electric field density, we are dealing with Gauss law, but for magnetic field density, we are dealing with ACL law, right? So, but the process is the same. So now let's assume, okay, to define the magnetic field density, first let's assume, okay, assume that the both medium is free space medium. Okay, same for here. Let's assume that for magnetic field also, electric field also, that the medium is free space medium. Okay, so when we say that free space for electric field, what will come out? What will come automatically to your mind? It is epsilon naught, right? Epsilon naught. But what will be for magnetic field density? It will be different, quite slightly different. Okay, so first of all, for electric field density, okay, for electric field density, if we discuss about electric flux, now we are comparing all the formulas, yeah. For the electric flux, it is represented how? It is represented E, right? Like this. For magnetic flux, it will be represented, magnetic flux, yeah, it will be represented as H. Same, but only instead of E, it will refer to H. Okay, and what are the formula for electrostatic field? The formula is, if you still remember, is equals to integration of D dot ds, right? And for magnetic field, the formula is also same. H is equals to, now instead of D, we will represent it as B. B dot ds. Okay, because magnetic field density, it is represented as B, and so we have to replace this D with B. Okay, but the what the rest is the same. ds dot ds, and this is also dot ds. Okay, now for electric field intensity. Okay, electric field intensity. Okay, where it is represented as E, right? But for magnetic field intensity, it is represented as intensity. Still remember, it is represented as H, right? And from here, for electric field density, this E, yeah, we can find, or we can define electric field density D is equals to epsilon naught, or we call it as permittivity times with electric field intensity times with E. But this is for, since that it is epsilon naught, so this is referring to the free space, right? Okay. However, for magnetic field intensity, okay, for electric magnetic field intensity, for us to calculate magnetic field density from magnetic field intensity, it is also same with electrostatic field. However, instead of epsilon naught, we will deal with mu naught h. Okay, and what are the value of mu naught here? Sorry, before we go to the value, what is mu naught here means? It means that permeability, yeah, permeability. Okay, permeability for free space, for medium in free space. So what the difference is only this part, yeah. For electrostatic field, we are dealing with permittivity, but for magnetic field, magnetostatic field, we will deal with permeability, where the value is also will be different with electrostatic field, which is 4 pi times 10 to the power of minus 7. Okay, 4 pi times 10 to the power of minus 7. Okay, so this is the value of um, permeability for magnetostatic field. All right. I think I don't have to repeat what is the value for epsilon naught, right? I think you should remember this. What is the value for epsilon naught? Okay. And next, for electrostatic field, what can we say for the Gauss law? For Gauss law, okay, we can say that close integration d dot ds is equals to q and close. Okay, and for magnetostatic field, we can say that closed loop integration B, which is magnetic field density, okay, dot ds is always equals to 0. Okay, always equals to 0. And for this magnetostatic field, electrostatic field, these equations, yeah, we can change to the point form. Okay, the point form of this equation is can be represented as del dot d, which is equals to rho v, and this is also we can change to point form where it will be del dot b equals to 0. Okay, so this del dot b here, this is another Maxwell equation. This here is another Maxwell equation, and this is Maxwell equation number 4. Okay, so up until now I have introduced to you 4 equations of Maxwell. Okay, let's look what are the equations. So this is the apa tu the summarize of Maxwell equations. Okay, so for example, for electrostatic field in integral form, I have divided here, yeah, in integral form and in point form. So for electrostatic field, okay, equation number 1. Okay, let's recall it together. Okay, for integration form, okay, d dot ds is equals to q enclosed, where this is a Gauss law, from Gauss law. Okay, and the point form of this is del dot d is equals to rho v. Okay, and Maxwell equation number 2 for electrostatic world is close integration of E dot dl equals to 0, and the point form of this format, integration format, is del cross E, del of curl of E is equals to 0. Okay, and for magnetostatic world, Maxwell equation number 3, closed loop integration H dot dl is equals to I enclosed. Okay, I enclosed here. So the point form of this format is curl of H equals to J. Okay, volume current density. And the last of Maxwell equation, which is Maxwell equation number 4 for magnetostatic world, is closed loop integration B dot ds is equals to 0 and del dot B is equals to 0. Okay, so these are all the summarization of Maxwell equation, and these are all the summarizations of what of electrostatic world and magnetostatic world. Okay, and from here I already showed to you how we want to define the magnetic field density from the magnetic field intensity, where there is a constant value here for free space, which is permeability mu naught here, where the value is 4 pi times 10 to the power of minus 7. Okay, and also we compare the electrostatic world and the magnetostatic world. Okay, and in this slide I showed to you the summarization of Maxwell equations from what we have learned from electrostatic world and magnetostatic world, from integration form and point form. Okay, for both. Okay, so all this while we learn. Okay, all this while we learn in a static motion. If you still remember, this is all in a static form, where we said that the time, why I said it is static, because we said that the time is 0. There is no relation of time. Okay, we assume that the time is 0. If you still remember, we ignore the time. However, later on, okay, after this, we will see how all these equations, how in a where there is a value of time, or there's a time relation, where we can say that time varying. Okay, when there's a changes of time, and that we will come to the end, or the final, which is the electromagnetic, which is the combinations of electric and magnetic world, which is electromagnetic. Okay, so this is this is later on we will move to the time varying, and then after that we will go to the electromagnetic, and that will be our final of EMT course. Okay, so far we have covered all the magnetostatic field and the electrostatic field, and I hope you able to get all the gist, from those two static world motions. All right, so that's all. I will end our lecture today. Okay, so I hope all of you will stay safe. Okay, stay safe, and if you have any questions that you want to ask, please you contact me. Okay, please inform to me, so I will explain to you. All right, so thank you very much, and assalamu alaikum.